Good morning. To introduce this topic, in the past, I've often done like a little bit of a matching game. So if you look at the notes that are posted in Teams, and I hope you remember that the notes are actually posted in Teams, that you can go and find the scanned copies of the notes that I do the lesson from, and you can look at them. But you'll notice that I have like column A and column B, and I have, it's pretty much like a little matching game. So you've got like exponents in some of the slots and radicals in some of the slots, and you're looking for a connection between the exponents and the radicals. And you might have been wondering in the last lesson, like, why is she doing exponents? And it's because exponents and radicals actually are related. Now, this year I am going to try something a little bit different. So if you're looking at that copy of the notes, just know that I am going to deviate from it for the beginning part of this lesson. And I want you to bear with me. I'm going to go through two exercises with this just to illustrate a little bit about what rational exponents are, where they come from, or how they're related to radicals. First off, rational means can be written as a fraction. And in this case, because you got like rational, we have the word ratio in there. And in this case, when we talk about rational exponents, what we mean is exponents that are fractions. Okay, that's what we're specifically referring to, as opposed to exponents that are integers, which is what we looked at in the last lesson. So you kind of start with the definition of exponent is it's the number of times something is used as a factor. And then we end up with like an exponent of 0, which seems weird. And then we get those negative exponents, which seems weird. And now we're going to have exponents that are fractions. Like this just seems like we're so far away from the definition of exponent at this point, but it all fits together and it really does all work. So bear with me for a moment. Let's say we have x to the 1/2. Okay. Now at this moment, you don't really know what x to the 1/2 means. How can x be used as a factor half of the time? That doesn't quite seem right. And, but just bear with me. I'm going to multiply that by x to the 1/2. Now, we know from our laws of exponents that if we multiply like bases, then we add exponents. So this would be x to the 1/2 plus 1/2. Okay, with me so far? On the right-hand side, 1/2 plus 1/2 is 1. On the left-hand side, I'm going to do something a little bit different. We know that the definition of squaring is multiplying by itself. So what I have going on right here is x to the 1/2 squared. I'll let you think about that for a moment. It's like one thing to hear it and write it down and see it. And sometimes your brain just needs a moment to like think about what it was you wrote down, because we multiplied it by itself. Now you can see that these are equivalent because if you multiply the exponents, which would be another law of exponents there, like 1/2 times 2 is 1. And so we're clearly still equal there. But I want to do something a little bit different. I want to think, how do I undo squaring? We undo squaring by taking a square root. So I am going to recopy this just for a little bit of clarity here. So I'm going to undo this squaring by taking a square root. Golden rule of algebra says that if you, whatever you do to the left side, you have to do the right side. So if I take the square root of the left, I have to take the square root of the right. Now, remember that the index on your square root is a 2. On the left-hand side, square rooting and square rooting undo each other, and I am left with the x to the 1/2. And here on the right, I have the square root of x to the first power, or simply the square root of x. Okay, and because you don't have to write the index of 2, and you don't have to write the exponent 1, but I do kind of want you to see that. And so x to the 1/2, where, I don't know, 2.5 minutes ago, we didn't really know what x to the 1/2 was or what it could mean. Now we actually do see what it is. X to the 1/2 is another way of writing the square root of x. Now I want you to pay particular attention to the position of the 1 and the 2. The 1 is the numerator of the fraction, and it is the exponent on the x. The 2 is the denominator of the fraction, and it is the index on the radical. I'll just let that kind of sit there for a second with you. All right, before we click and move on. Now, that might be interesting enough, or maybe not interesting. I don't know how you feel about it, but we're going to try it again. This time we're going to do x to the 1/3. Okay, so I have x to the 1/3 times x to the 1/3 times x to the 1/3. So we have like a different fraction there. And we know from our laws of exponents that if you multiply like bases, you add the exponents. So on the right hand side, I have x to the 1/3 plus 1/3 plus 1/3. On the right hand side, 1/3 plus 1/3 plus 1/3 is just 1. On the left hand side, when we take something and we use it as a factor 3 times, that is the same as cubing it. That's the definition of cubing. So what am I cubing in this problem over here on the left-hand side? I'm cubing x to the 1/3. Now, as before, I'm going to recopy this. This is for just kind of keeping the different lines of the work like clean and separate here. If I want to undo cubing, I would use a cube root, which like a couple weeks ago, we didn't really know what a cube root was. Maybe you'd seen it, maybe you've studied it before, but now we're sure we know what a cube root is. A cube root undoes cubing. So on the left-hand side, I'm going to take a cube root. Golden rule of algebra, whatever you do to one side of the equation, you have to make sure you do to the other side. So I have to cube root the other side as well. On the left-hand side, the cube root and the cubing undo each other, and we are left with x to the 1/3. On the right-hand side, we have x to the first power, and we're taking the cube root. Now, notice again on this, notice the position of the numbers. The numerator is the exponent. The denominator is the index. And now we could keep going. We could do x to the 1/4, x to the 1/5. We could keep going with this. We could also tinker around with the numerators, try some different things there. That'll get a little bit more complicated because then it doesn't necessarily add up to 1 the way we would like it to. But we could keep playing with it. And what we would eventually come up with is this key idea. And the key idea goes like this. If you have a radical with a particular index and you're taking the radical of something raised to an exponent, that can be rewritten as x to the a over b, like so. Notice the positioning of the numbers. The index matches up with the denominator, which we saw over here. The index matched with the denominator, okay? And we saw it here. The index matched with the denominator. And so generally speaking, the index matches with the denominator. And the exponent matches with the numerator, okay? And that's how they line up. It has nothing to do with which number is bigger or which number is smaller. It's everything to do with the positioning of the numbers. Now, this next line might make you a little bit uncomfortable. This also works if the exponent is outside of the radical. Okay? And I actually hope that that makes you a little bit uncomfortable. Okay? I actually hope that you are bothered by that, because in mathematics, we generally can't just move stuff. Like you can't move numbers from like a numerator to a denominator unless there's like a clear reason, like you're changing a negative exponent to a positive or something. You can't move stuff from like around in an equation unless there is a solid reason why it's okay to make that move. So when I take an exponent that's under a radical and I suddenly move it outside the radical and I'm telling you that it's the exact same thing, I hope that there's a part of you that wants to say, wait a minute, Miss Taylor, why is that okay? Because that kind of defies like what's normal. I can show you why it's okay. I think I might save it till the end of this lesson just because I don't want to clutter up like the middle of the lesson, and I know not everybody is going to be interested in it. So what we've got here is this idea. Every radical can be written as an exponent. And vice versa. Okay, so, and vice versa, which means it goes the other way. So every exponent can be written as a radical. And so we have this way of being able to rewrite things in a different form. Which is why in the middle of a unit on radicals, we all of a sudden had this lesson on exponents, because we end up going through this process that uses the rules of exponents and then ties the exponents into the radicals. So there's like a reason for that. Now, this is just like a fact that you have to memorize. If you do enough of your homework, you'll just memorize it. Okay, like you will just get it memorized, because that's what happens when you keep writing stuff down. It's amazing. So I'm going to go through a bunch of examples on this, so you can see what they look like. They kind of range from the really simple to much more complicated, like most of the stuff that we do. And we're going to work in both directions. So for the first one, if you were given x to the 1/5, the directions might be write that as a radical. It means you're going to change the form. You're going to write it in an equivalent way. And so you'd set up the radical, and then it's just a matter of putting the numbers in the right place. So the index of the radical is going to be the denominator of the fraction. And then the base of the exponent is going to be the radicand, what goes under. And then the numerator is the exponent. And you may or may not have to write it. So like x to the first power, like you don't really need to write x to the first power. But you can. There's nothing wrong with writing x to the first power. Okay? Or if you want to, you could just write the 5th root of x. I think that's right. We'll just put the word or in there. Okay? So that was pretty straightforward. Now let's look at another example. This one is x to the 2/5. So we haven't really looked at one that had a different numerator other than 1, but let's go ahead and look at one that has a numerator other than 1. But math is consistent. So when I give you a nice little rule like that, you know that that rule is going to be consistently applied. It's just you have to kind of see all the different variations of it before you feel confident. So we set up our radical. The denominator of the fraction is going to be the index of the radical. The base of that exponential is the radicand, and the numerator is going to be the exponent. Now you could also write it this way with the exponent on the outside. And I tend to prefer the first way, but it comes in handy. The fact that you can kind of move it around a little bit can sometimes allow you to do like an easier part of the problem first. All right, so let's look at going in the other direction. Let's look at example 3. Suppose you had a radical. We got like 7x here, okay? Now, in the directions here would be take this and write it as an exponent. And for those of you that eventually go on to calculus, you will do this version of the problem over and over and over again. In calculus, there's something that you do with your functions that you do not want to do it with a radical. What you want is an exponent. And so you take all your radicals in calculus and you change them over to exponents so you can do this particular thing. So to get this, we have to figure out what's my exponent and what's my index. Well, in a square root, the index is a 2. The exponent in this case is a 1, and I'll let you kind of digest that for a moment. You've got 7x, and the whole thing is being raised to the first power. Okay, so when we go to rewrite this, we're going to have the base is going to be the radicand. The 7 and the x are both lumped together because they were both together under the radical. The numerator of the fraction is going to be whatever that exponent was, and the denominator is going to be the index, like so. All right, next one. This gets into some interesting stuff. All right, so this would be the 4th root of c squared. Okay, so we have the 4th root of c squared. And you can think about like simplifying your radicals. You actually can't simplify that. You'd be looking for groups of 4. And you don't have a group of 4. You only have 2 c's there. But that's not the directions here. We're going to change it over to an exponent. So we're going to take the c then the numerator of our fraction is going to be whatever that exponent was. And the denominator of the fraction is going to be the index. Okay? And 2/4 actually simplifies to 1/2. Pretty cool, huh? And sometimes you might even change it back to a radical. Okay? So you could actually go back and say, all right, now I can do the square root of c to the first power, or just the square root of c. And so you're able to figure out that the fourth root of c squared is actually the same as the square root of c. So you got like all these different ways that you can kind of juggle them around. Last of the examples. What is the last example here? Example 5. This is the cube root of 5xy to the 6th. Ooh, this is so cool. I'm actually liking this. I'm going to do this 2 different ways because I am inspired. I'm having fun with this. I hope you guys don't mind. Okay, so first way we're going to do it is we're going to change it to an exponent. Now, years ago, I was teaching this lesson, and I kind of did this accidentally, where I always made the index like the bigger number. And if you look at all these examples, you'll notice that the index is bigger than the exponent. Index is bigger than the exponent. Index bigger than the exponent. And I had a student raise his hand and say, okay, so the smaller number is always the numerator and the larger number is the denominator. And I'm like, oh, no. It has to do with the position of the numbers, not their relative size. But I was so glad that the student spoke up, because without even realizing it, I had picked a bunch of examples that were kind of confusing and led the student to the wrong conclusion. So now when I teach the lesson, I try to make sure I have at least one example where the index is smaller than the exponent, so that you guys see that like that actually can happen. And it's okay. So please speak up. If you think you're seeing a pattern, it makes me a better teacher, and I always am trying to be a better teacher. So when we go to rewrite this, here's the base. We have like the 5xy, and they're all kind of grouped together, like 5xy like that. Then we have our exponent. The numerator of the exponent is going to be whatever the exponent under the radical was. And the denominator of the exponent is always the index, even if that gives you an improper fraction. Okay, so that was like the conclusion that the student drew that was not the right conclusion. It's okay to have an improper fraction. Now watch what happens with this. 6 divided by 3 is 2. And now we could actually go further with this. Now that we've gone through our laws of exponents, we know that 5 squared is 25. And then we have x squared and y squared. Now, just for fun, because math is fun. Okay, sorry that if I'm doing that to you guys. A couple of lessons ago, like the beginning part of this unit, we talked about simplifying radicals. And we know that we can like expand this out, so we can kick in our laws of exponents, and we can expand that out, and then we'd be looking for groups of 3. So let's just see what happens with that. If I have 5 to the 6th power, that's going to give me 6 5s. Okay. 1, 2, that's a 5. 1, 2, 3, 4, 5, 6. And then I have 6 x's. 1, 2, 3, 4, 5, 6. And 6 y's. 1, 2, 3, 4, 5, 6. Because it is a cube root, I'm going to be looking for groups of 3. Here's a group of 3. Here's another group of 3. Here's a group of 3. And another group of 3, which we know is going to make that x squared. Here's a group of 3. And another group of 3. And then 5 times 5 is 25. And lo and behold, we have the same answer. And maybe this makes me super nerdy, but I think it's really cool that we can do the same problem, try to simplify it 2 totally different ways, and we end up in the same spot, which just shows you there's more than one way to think through these problems, and that's why we want to get the fundamentals down. So we have a couple of practice problems for you to work on, and really it's just about learning where to put those numbers. So I'm going to put those practice problems up here. I'll give you a few minutes to work them out, and then we have a couple more concepts at the end of this lesson. So We're going to do 36 to the 1/2, t to the 3/4, the cube root of 2x all squared, and the square root of xy. So I'll pause the video at this point and give you guys a chance to do those out. And here are the answers so you can check your work. First one is the square root of 36. If you took that one extra step and said 6, that's fine too. Okay, so 36 to the 1/2 is the same as the square root of 36. We've got t to the 3/4. That would be the 4th root of t to the 3rd. And you could also opt to write it with the 3rd on the outside. Okay, that's okay as well. Number 3 is 2x lumped together. Okay, they have to be lumped together to the 2/3. And if you didn't put the parentheses in, please add those parentheses into your scratchwork now. They are important. They were grouped together under the radicals, so they have to be grouped together for the exponent as well. And then the 4th one is xy all grouped together to the 1/2. And now it's totally okay to have some issues with that too. So if you got the first 2 correct and then made mistakes on the second 2, that's because the second 2 are a little bit harder than the first 2. So that's okay too, as long as you learn from the mistake. So this actually allows us to do a little bit more with our radicals. And I'll give you an illustration of what we mean when we say we can do more with the radicals. So take, for example, this. If you had the 4th root of 6 times the cube root of 6. I don't know why I doubled up on my multiplication symbol, so that's kind of weird. Up until this point, you can't do that multiplication because the indices don't match. And I said it was really rare that the indices don't match. But when they don't match, now we have a way around it. So we've got the 4th root of x times the cube root of x. So I'm going to go ahead and change that. Remember, the exponent on the 6's is 1. So this will be 6 to the 1/4 times 6 to the 1/3. And we don't have a way of multiplying the radicals, but we do have a way of multiplying the like bases using the exponents. And we know that we will add those exponents together. Now, I would love to believe that everybody in here is like perfectly comfortable and capable with adding those fractions, but I know that's not the case. So we'll go through this. If you were taking 1/4 plus 1/3, you do need a common denominator. So we have to change the way the fractions look, but not the value of the fractions. And the way we do that is by multiplying by the number 1. We're going to multiply the number 1 to the 1/4 and the number 1 to the 1/3, because we know that multiplying by 1 won't change it. The version of 1 we're going to multiply here is 3/3. And I picked the 3 because it was the denominator of the other fraction, and I know I can get a common denominator that way. Multiplying across, 3 times 1 is 3, and 3 times 4 is 12. Over here, the version of 1 that we're going to multiply by is going to be 4/4. And I got that from the other denominator because I knew I could do 3 times 4 and get the 12. So 1 times 4 is 4, and 3 times 4 is 12. And if you look at these two fractions, 3/12 is the same as 1/4, and 4/12 is the same as 1/3, except now we have the common denominator, which is 12, and we get 7/12. And so this ends up being 6 to the 7/12. You might change that back over. I honestly don't really care if you do, like the 12th root of 6 to the 7th. Now, sometimes students will ask me, like, is it always you would just multiply the indices together and add them to get like the exponent and multiply them? I don't think so. I would have to do a lot more examples, and I never do that many examples because those kind of problems aren't super common. Yeah, they're just not super common. But be wary of it. Just try not to take any shortcuts with that. And if any of you would like to do some research on that, let me know. All right, last thing that you might see is a decimal exponent. Because now that we know that we can have fractional exponents, you might see a decimal. So you might see something like x to the 1.2. And in fact, in science class, you actually will see that pretty frequently. You'll see exponents that are decimals. Now, the way I like to process this is I like to go back to what that number is. That is 1 and 2/10. If you think way back to like, I don't know, 4th grade or something, when you start learning decimals, 1 and 2/10. So that would be 1 and 2/10 as a mixed number. And then to change from a mixed number to a fraction, you would do 10 times 1 plus 2, which is what, 12 over 10. That actually simplifies to 6/5. And so you end up with 6/5, or you could write it as the 5th root of x to the 6th, or, oh my gosh, it just gets so much more fun. You could do, you got your 6 x's under there, okay? And you're looking for a group of 5. So it could be x times the 5th root of x. There's just so much fun stuff that you could do with that. All right, there are 2 more practice problems in there, and I'm debating whether or not to do them or to just kind of take you through why it's okay that for the A to move, and I think I'm leaning in favor of the A. So I'm going to do that workout on the next slide, and then I'll just talk you through it briefly. All right, here's what it looks like. And if you notice, like on the far left, I have the bth root of x to the a, where the a is inside the radical, and way down here at the right end, we have the bth root of x, and now the a is outside. And it's all connected with equal signs, which means that every step along the way should be equal to the step before it, which means that the beginning should be equal to the end, which is why you can move the a. In the first step, all I did was change this over to a rational exponent. So we have the numerator and we have the denominator. Now, this step right here might throw you a little bit. I said a over b is equal to 1 over b times a. And pretty much what I did was I kind of split up the fraction. When you multiply fractions, you always multiply straight across. So 1 times a would be a, and b times 1 would be b. And what I did was I just kind of pulled the a out. That's the part that's a little bit weird, but hopefully you agree that like it's true, even if it's weird. And you don't have to write the a over 1. Okay? Now, what I did right here was I know my rules of exponents, and multiplying exponents comes from raising a power to a power. So I just kind of grouped that together and said, let's take a to the 1 over b and x to the 1 over b, raise that to the 8th power. And that would mean we'd multiply the exponents. Then I took this part right here and changed it back into a radical. So you'd have the bth root of x to the 1st power. You like had the exponent of 1 there, but you don't need to write the exponent of 1. Yeah. And now you've got the a on the outside. So you can kind of tell when the parentheses pop up. So it's pretty much just using the changing it over to a fraction. It's using just how fractions work, then using one of the laws of exponents, and now you can see it come back. I'm going to put the other 2 practice problems up there because I'm not quite out of time, but I have a feeling that when we do this in class, we probably will be out of time. But I don't know that as I'm recording it. So I'm going to put the practice problems up there, and we'll do in class whatever we need to do in class. But here are the 2 practice problems. And the first one, the directions are to multiply those by changing them over to exponents. And the second one is to write that as an exponent and then as a radical, kind of like the other examples I did. I'll put the answers up on the next slide just for anybody who's watching at home or is like doing this as a refresher and just wants some extra practice. But again, I have a feeling we'll be out of time in class. All right, here are the answers and the solutions. So the answers are down here at the bottom. 5 to the 7/10 or the 10th root of 5 to the 5th. Okay, either or, just follow directions. And then this one as a unsimplified radical would be the 10th root of y to the 23rd. Or if you simplify it, you're going to bring out two groups of 10, and then you'll be left with 3 left over. So y squared times the 10th root of y to the 3rd. So for anybody doing those at home, there's like the work and the solutions. And I only have 15 seconds left in this video. So hopefully this was good, and I will see you next time.